So fellas, how are you doing today? Welcome to my channel. Today we are going to be talking about solving a hard problem on LeetCode. The problem is finding median from the data stream. So the problem description says median is the middle value in an ordered integer list, as we all know. If the size of the list is even, there is no middle value. So the median in that case is the mean of the two middle values. Now the middle values in the sorted list will be like whatever the values there are, it doesn't matter. The number of values and their position in the sorted list matters. So we are going to speculate what all options we can use to solve this problem. Firstly, something like a balanced binary search tree comes to our mind because the top of the or the root of the balanced binary tree is always a median. Um, but like balancing and everything is a time-consuming task. So there are collections-based classes in Java which are based on balanced binary trees like tree map and tree set. But neither of them can be used in our case because the tree set ignores duplicates, hence we lose count of the elements that we are having, which are incoming. And even the tree map, which sorts the elements by its keys, is not suitable because in that case we'll have to put the values as keys and in order to have them sorted. But the keys there are also again a set, so they are not allowed to be duplicates. So we will go and think about something which helps us solve a problem. If we, in a most naive way, we can go ahead and sort the available list of numbers that we are having, see the count of the numbers we have seen so far, and pick the n by 2th number or the two of the middle numbers and see their mean. But then that is very time-consuming task because mostly because sorting every time we see a number, sorting the entire list is like not very efficient solution. So it will be n into n log n, which is like waste. So if we want to deal with large number of inputs, we have to see an alternative solution. So what comes to our mind is actually we need the middle two elements, right, or the middle element. We don't even care about what the other elements are and what order the other elements are coming in. So we don't need them all to be sorted. We just have to keep a track of the middle element. And so there's a very good data structure that comes to our mind, which deals with exactly that. It is a heap, right? But then how will it help in our case? We can have two heaps to keep track of the lesser elements and the greater elements than the middle element in the heap. I'll tell you just now how to do that. So since this is a hard problem, it is typically, and a lot of upvotes it has got, I thought it's a good problem to go through and explain you how to solve it. So what if we can imagine a pair of heaps in such a way that the less than the middle elements are in a max heap and all the elements greater than that middle element are in a min heap in such a way that their tops point to the middle two elements, or one of the heaps has the middle element actually the answer. So in order to attain that, we're going to frame a solution in such a way that we keep the track of the middle elements. We don't lose the count. So our heaps should always have the root as the middle elements, no less, no more. For that to happen, both the heaps should have equal or balanced, approximately equal, give and take a one element, they should be balanced in their sizes. So to make the picture more clear, you'll see as we go through how to solve it. So we have to actually design the data structure in such a way that we provide an add num, which adds an integer to our data structure, and find median, which returns at any given point, which returns the median of the elements seen so far. So yeah, so here we design our data structure. So yeah, since we are designing in Java, heaps are something which are the underlying data structure behind priority queues. So a priority queue constructed with the default constructor is a min heap by default. We can also create max heap by providing it a comparator, and that's how we'll do it. Let's see how. So let's take a priority queue of integers, lesser heap, let's call it that, and we'll take a priority queue of greater values as well. In the constructor, we are going to assign the greater and the lesser their actual objects. So lesser is equal to new priority queue of integers. Yeah, damn, it will help. Now this is a max heap which is not provided by default. So here we have to provide the the comparator, right? So it also has to take as a first argument the initial size. Let's have it as integer 10, and we'll provide it as the comparator using lambda. Oops, yeah, which returns 2 minus 1. Good enough. Then the greater will be a new priority queue, again of integers. Now this time we have it already provided by the default constructor, so we don't need any other thing. This is yeah. So once we are done with this, we're done with the construction, we'll come down and add a number. So adding a number has to take into account the balancing effect of the heaps as well, and we have to see which heap the number has to go to. So we can take out of any of the heap, both of the heap, we can take any one heap and consider its topmost element as a reference element, compared to which we'll decide whether to keep our element in the lesser value heap or the greater value heap, right? So for the reference value to be always there, we have to be sure that the value is always there actually. So when there are, so in the first case, even if we have, let's consider that heap to be the lesser heap. If lesser dot size is equal to 0, which will be initially, we'll assign that value, the first value actually, to the lesser heap. Or also, if the size is not 0, we already have a reference to element, and we'll compare our number which we've got. If that number is less than the reference element, which is lesser dot top, lesser dot peak, yeah, then also we have to insert our num in the lesser heap. Lesser dot add num to it. Yeah. If not that, then we fall into our else case. In that case, we'll put our number into the greater heap num. Fine. Once we are done adding our element, which is done one by one every time as an element comes, once we've added our upcoming element, we'll have to balance out the heap. Yeah, so just like that, we are going to do it in this way. So if lesser heap has if the elements are equal in size after the insertion, then we are done. We don't have to do any extra steps. So we'll mention that if lesser dot size, right, is equal to greater dot size, right, then we are done and we simply return. Otherwise, if lesser dot size, so actually if the heaps are equal in size, that's fine. Also, if there is a difference of 1 in the sizes, then also it's fine. We don't have to do anything because we can have odd number of numbers, right? In that case, either of the heap will have at least one more than the other. So we should do it like this actually. If lesser size minus greater the size and the math.abs absolute value of the subtraction of the values is less than equal to 1, then we are fine with it, right? Otherwise we are not. Then you have to do the balancing act. Yeah. So if the lesser dot size is less than greater dot size, right? In that case we'll have to, so in that case the difference is definitely more than 1, and also lesser is lesser value and the greater is like having 2 or more elements than lesser. So if the lesser size is less than greater, we just have to take the element out of the greater and put it into lesser. Lesser dot add greater dot whole, right? Whole, yeah. Whole thereby removes the element as well out of the greater. Yeah. And we are done with it. We can simply return. But we don't want to do it like that. We also want to add in an else condition, which says if the lesser size is not lesser, which means the greater size is lesser because equal to and a difference of 1 is already handled, greater than add lesser dot whole. Yep. And in the end, we have added our number. We have maintained the condition of our data structure. The sizes should be back between the difference between the heap sizes should be maximum of 1, and now we are going to find a median. Now this is going to be pretty simple. If the sizes are equal, then we have to find the mean, else we have to return the value of the greater, the topmost value of the greater element, so greater heap. So if lesser dot size equal to greater dot size, simply return lesser dot peak plus greater dot peak by 2. So now that we are dividing, we also have to make sure that it's okay. So it's an integer division, so that will be truncated in order to avoid that, because we want to take care of the doubles also. See here in this case, for example, we are returning a double without truncating the decimal parts. We have to convert it to a double as well, any of the two, and we are done. If this is done, then if this is the case, we'll return this. Otherwise, if not yet returned, we'll see if lesser dot size is greater than greater dot size. That's what we have to return then, the top of it. So let's return let's return lesser dot peak without calling it. Yeah. Else, actually else is not needed also. If not yet returned, we'll simply return greater dot right. That looks good. A rough go through with the solution. Fine. Right. Let's see how it fares. Okay, it says. Okay, so actually we've done a plural, which is not an actual class. Not work. There was a little type over there. Good. So this passes, and let's see what the final submission of all the test cases says. Success. Cool. So that's how we go about it. So many a times you're asked this question in a flavor of something like how to do this problem without using any of the pre-built classes that Java provides to us. So something without using a collection class like priority queue would be to easily come up with a array-based priority queue of yourself. So in that case, you'll have to provide the functions which you are using for lesser and greater here, like you might want to provide add, size, peak, and poll. So that should be very trivial to implement, not a very hard task or rocket science. You just have to make sure that when you're adding an element, the element has to be added towards the final. So binary search, a binary heap is actually used to implement a priority queue in the most optimal manner. And a binary heap is nothing else but a complete binary tree with all the levels filled, apart from possibly just one option of the last level, which may be partially filled, but it is always most filled towards the the more left you go, you'll find all the filled elements, and you can just add on more elements towards the last level towards your right. So just add an element to the rightmost and go up the parent chain and see where it fits. If it is a min heap, see if there are no parents which are more than that parent, and let it stop where all the elements above it are lesser. And similarly, vice versa for max heap. If you just insert it in the last level and move it up the parent chain and see where it fits in such a way that it is relative to its children and parents hierarchy, and all the elements above it, its parents are greater than it, and so on and so forth. So that can be done with an array list, actually, in amortized ON time. So yeah, talking about the complexity, this addnum is using the heaps add function, which is log n in operation. So and there are no loops, so this is an big O of log n solution. And this function, which is called in time in the middle, is actually O1, because this makes use of only size and peak elements, which are constant time operations in our priority queue. So yes, we are done with it, and let me know how it goes. And by the way, I'll also provide the solution of doing it without any pre-built collections class, as well as the solution on my blog. So go through that and let me know how it goes for you. If you ever get stuck, just comment to me. I'll reply and help you sort out your issues. So if you need anything else, just comment, and we'll be moving you forth. Thanks for watching. Bye.